All right, rotations and torque. So what we're going to do is we're going to talk about rotations. We're going to start off not by talking about torque, but what we'll talk about instead is we'll talk about the rolling kinetic energy of your object. So it might not be surprising to notice that if you have a ball and it's sliding at the same speed as another ball that's rolling, the rolling ball has more energy because all of the atoms are not just moving this way, they're also rotating around the center here. So that actually gives it a little bit more energy than usual. So I'll do an example of that in the examples, right? But right now I'm just going to talk about why that is. So, I mean, that is why it is. It's because of that. So what I've just said is that a rolling object has extra energy. So that the normal kinetic energy is this kT, that's a translational kinetic energy plus an additional rotational part. So this is the same one that we've looked at before. That's the 1/2 mv squared. And then we have this rotational part over here, and that has a similar expression. That's 1/2 I omega squared. This is your angular speed. Okay, and this is what we call the rotational inertia. So the rotational inertia is a little bit different from the mass, but it's got the same purpose in this equation, right? So here we have the angular speed, right? And here we have your speed squared, and the mass has the same purpose there. So you might guess that this angular or rotational inertia has the same sort of properties. It has the same sort of meaning as this guy, and it actually does. Rotational inertia is your resistance to increasing your rotational speed, just the way your mass is your resistance to being pushed, right, to increasing your regular speed or reducing it. So your mass reduces changes in speed, resists acceleration. The same thing with rotational inertia. Your rotational inertia is your resistance to being set to spin or to stop spinning, either way. So rotational inertia resists angular acceleration. And I will not have you do anything where you have to sort of calculate what that rotational inertia is. The rotational inertia always has some sort of form like I equals some number times mr squared, or something similar. There'll be a length here, a mass, and a number. And that number is hard to figure out, so you just look it up in a table. So there's a table in your book, so if you need to figure it out, you just look at that number in your table. So this number here increases depending on how much mass you have towards the edge of the object. So if you have mass concentrated at the edge of your object, then you have a larger inertia, larger rotational inertia. So let's say you had a tire, which is basically all your mass is at the edge here, and then you had a rubber cylinder, a thin rubber cylinder, like that. So they have the same mass. This guy's going to be heavier. This guy and this guy are just as heavy, right? This guy's going to have a greater moment of inertia. It's going to be mr squared. Rotational inertia is mr squared. The mass times the square of the radius, whereas this guy is going to have less of that. It's going to be 1/2 exactly that. That won't always be true for a sphere and a circle, or a sphere and not a circle, but a sphere and a hollow shell. The hollow shell has 2/3 mr squared, and the solid sphere has 2/5 mr squared. So it's not always exactly a factor of 2, but it happens to be for something like, it looks sort of like this, which is sort of a tire. Okay. So you'll just have to look those up when you have to look them up. That's the way of the world. Okay, that was actually A, not 2. I forgot my... format. Now we have to relate the angular speed. I don't remember if we did this before, or we probably did, but we probably didn't spend too much time on it. The angular speed is proportional to the linear speed for a rolling object. So for a rolling object, what's going on is that as you move this way, you have to turn exactly that distance as you move. So if you're starting off here and then you move this distance, and you have to end up exactly here, so that when you're here, this point is there and this other point over here is up there. So as you're going along, you have to do exactly as much distance around as you go forward. That makes sense? That means that as long as you're touching the ground, you've always got one bit touching, and you're not getting any slipping, right? You don't want to slip. Like if you're on a bicycle, if you start slipping, that's called skidding, right? You don't want to skid. You don't want to lose control, basically, right? If you're hydroplaning, then your tires are no longer connected to the ground, which means your tires and the ground are sort of moving at different rates. Again, that's really bad for your control, right? And it's something that can cause a lot of damage. So you want your tires always to be rolling. We care about rolling a lot in physics. Well, we do care about rolling a lot everywhere. And so that rolling is going to sort of keep how far you go around connected to how far you go linearly. And that is going to be your speed equals omega r. And we're going to see this in the example where I'm going to compare an object that's rolling and an object that's sliding. You know, the same object's rolling and sliding basically, and you'll see that you get an additional amount of energy from this rolling motion, you know, as this guy goes along like that. And it's going to be completely comparable because basically everything in here means that this and this are both functions of v and m, right? The moment of inertia is a function of m, v is, or omega is a function of v. So this and this are completely comparable. And as long as you know the radius of your object, then you can rewrite these and not have to worry about it. All right? So that should be enough to get you started on rotations. We're just going to look at rolling first, and then we'll talk about some other stuff in just a moment. All right? Bye now.